In the last lecture, we found that uncertainty principle points out a fundamental flaw in the Bohr model. What was that flaw? That if you want to have a definite orbit, you need to know the position and momentum of the electron simultaneously. This is not possible because of uncertainty principle, and therefore, we cannot talk of definite orbits. We can talk only of the clouds of electrons, and we can talk of the position of the electron in terms of probabilities. That was the flaw in the Bohr model pointed out by the uncertainty principle. Then we discussed the discovery of neutron, strong nuclear force, because if there are protons in the nucleus, they would repel each other and they would break the nucleus. But it was found that there is very strong force acting between the nucleons, and therefore, nucleons are able to overcome the Coulomb force between them. And then we studied absorption of neutrons by nuclei, and some of the examples are given here. And lastly, we found that neutrons can trigger fission reaction in the uranium atom, uranium 235. So, in this case, in the lecture today, now we shall talk of first atomic number and mass number. In fact, I have already hinted at this atomic number and mass number. Mass number is the total number of nucleons inside the nucleus, and atomic number is equal to the number of protons in the nucleus, because atomic number is equal to the charge of the nucleus, so number of protons, and mass number is the total number of nucleons inside the nucleus. So, this is the these two quantities we shall make use of when we do nuclear reactions. So, hydrogen nucleus was simply a proton, helium nucleus was now understood to contain 2 protons and 2 neutrons. The number of protons in the nucleus determine the chemical properties of the atoms. It is called the atomic number, that is the number of charges, denoted by Z. The total number of nucleons, protons plus neutrons, is called the mass number of the nucleus, denoted by the symbol A. So, we shall have this symbol X with A and Z. A is the mass number, Z is the atomic number. That is, for example, helium is represented as He with 4 as mass number and 2 as the atomic number. Here is the picture of the atom. I mean, imagination. There are 4 nuclei, 4 nucleons, 2 protons and 2 neutrons, and there are 2 electrons. We do not know where they are, because uncertainty principle does not allow us to know the position very precisely. So, this is a cloud of electrons, and the 2 electrons, this is the probable position of the electrons. So, we have 2 neutrons, 2 protons in the nucleus, and in the atom we have clouds which contain 2 electrons somewhere. That is the picture of the atom. Now, so far we have progressed only to helium. Let us see what happens if we go further, say Z equal to 3. The nucleus of the next element in the periodic table, lithium, contains 3 protons and 4 neutrons. Its atomic number is 3 and its mass number is 7. The mass number is approximately equal to the atomic weight of the atom, not exactly, but approximately. More accurate term is the atomic mass, but historically the term used is the atomic weight. The atomic weight of lithium is 6.941 U, is the mass of a proton approximately, or a neutron. We shall define this more precisely. The atomic weight of lithium is 6.941 U, while its mass number is 7. So, why do not we have this 7 here? What is this difference due to? One reason is the existence of more than one isotopes of lithium. We have already learnt what an isotope is. Isotope is a nucleus with different mass number. Besides lithium with mass number 7, there is another isotope of lithium which has mass number 6, and it has 1 neutron less in the nucleus. So, when these two are mixed, then the atomic weight of lithium is 6.941. U is the international atomic unit. The atomic weight of atom is defined as the weighted average of the mass number of all its isotopes. Both the isotopes lithium 7 and lithium 6 occur naturally. Former has abundance 92.5%, that is lithium 7, while the latter, that is lithium 6, has abundance 7.5%. Now, if you average them, atomic weight becomes 6 into 0.075 into plus 7 into 0.925. This is 92.5%, this is 7.5%, and if you add, you get 6.925 U. The much of the discrepancy between this value and quoted value 6.941 is due to the abundances taken being approximate. We have taken 92.5% and 7.5%, they differ slightly from these numbers, and that is why the actual number is 6.941 and not 6.925. Say for example, iron has 4 naturally occurring stable isotopes with the abundances given below. Iron 54 has abundance 5.8%, iron 56, which is the most stable one and most abundant, has abundance 91.72%, and iron 57 has abundance 2.2%, and iron 58 has abundance 0.28%. So, you can now find the atomic weight. It is 54 into this, plus 56 into this, plus 57 into this, plus 58 into this, divided by 100. So, that is therefore, the atomic weight of the iron nucleus, 55.91 U. What is the radius of the nucleus? We have seen that nuclei are composed of many nucleons. These nucleons, bound by strong nuclear force, make most nuclei spherical. You see, there is a very strong force, and therefore, the nucleus tends to be spherical. Just like Earth or other planets or stars, because of strong gravitational force, they tend to be spherical. So, because of strong nuclear force, nuclei tend to be spherical. So, if they are spherical, what is their radius? That is the question we are going to discuss. Earlier estimates of the size of the nucleus were made by Rutherford from scattering of alpha particles. As mentioned, the size of the nucleus was found to be about 1 Fermi, 10 to the power minus 15 meters. Scattering of other particles such as neutrons, electrons can also give definitive information about the size of nuclei. Electrons are particularly suited because they are very light and they can penetrate. Electrons are particularly suited for this purpose. They do not interact with neutrons. By interacting only with protons, they can trace the charge distribution of the nucleus. You see, there are neutrons and protons. These electrons, they just ignore the neutrons. They do not interact with them. They interact directly with protons, and therefore, they can give us information about the distribution of charge inside the nucleus. And from that charge sphere, we find the radius of the nucleus. Electron scattering of the nucleus, calcium for example, gives charge distribution of the kind shown here. This is the kind of distribution, and it is modeled by this equation, rho r is equal to rho 0 by 1 plus e to the power r minus capital R by a, and in this equation capital R is the radius of the nucleus. R is the distance from the center and capital R is the radius of the nucleus. Once again, this is the distribution, this charge distribution, and this is the radius of the nucleus, and it can be shown to be equal to 1.2 into a raised to power 1 by 3. A is the mass number. So, the data can be fit to this radius. Radius is equal to 1.2 into a raised to power 1 by 3 Fermi. So, this is the radius of the nucleus. The volume is 4 pi by 3 r cubed. So, 4 pi by 3 cube of 1.2 into a, because here it was a raised to power 1 by 3. So, when you raise it to power 3, it becomes a. So, that is the volume of the nucleus in Fermi cube. Notice that the nuclear volume increases with the mass number, you see, proportional to a. So, as a increases, as you go to larger nuclei, the radius also increases. The mass of the nucleus is obviously A multiplied by the atomic mass unit U. You remember, I told you that I will define this a little later. U is what is known as atomic mass unit. How do you define that? The atomic mass unit is defined as 1/12th of the mass of the most abundant isotope of carbon, that is carbon 12. Carbon 12 gives us 1/12th of that gives us 1 atomic mass unit. It is approximately equal to 1.66 into 10 to the power minus 27 kilogram. That is, I told you, it is approximately equal to the mass of the proton. So, the mass of the nucleus, so this is the volume, the mass of the nucleus, then this is the volume, it is approximately equal to 1.66. The number of protons in the nucleus determines the chemical properties of the atom. It is called the atomic number of the elements, denoted by the symbol Z. The total number of nucleon is the mass number, and you see, I think this is the volume of the nucleus. If we divide by the, if we want the relation between mass and volume, is density. So, if we divide the, if we want to find the density, then we will want to find volume, mass per unit volume, that is A by V. A is the mass and A by V, and you can see that this will turn out to be a constant quantity. So, the density of the nucleus is independent of the number of nucleons. A nucleus is said to be unstable if it breaks up spontaneously to form a different nucleus. You see, we have, say, nucleus X. If it spontaneously breaks up and forms a nucleus Y, we say that this nucleus X is unstable. In the process, the unstable nucleus may emit particles. Going from X to Y, it may emit particles like alpha particles, protons, neutrons, electrons, positrons, and photons. The process of decay of a nucleus is characteristic of the nucleus and is characterized by its half life, the time in which the initial amount is reduced to half. You see, if we start with, let us say, 1 gram of a particular material, and after some time it reduces to half, then this time is called the half life of the nucleus. So, half life is the time, we shall define it more carefully. Half life is the time in which the activity reduces to half of the original value. Here, this is how the decay takes place, this exponential, and you can see that this is the amount of substance. So, this is 0.5, this is 0.5. So, it will become 0.5 at this time. On this scale, this is 0.7 units. This is arbitrary scale, this is also arbitrary scale. So, this particular nucleus, the activity reduces to half in this time. So, this is therefore the half life of the nucleus. Notice that the mass and charge are conserved in the nuclear process. I have showed you earlier also in the last lecture, we found that if we write down a nuclear reaction, then the mass on this side as well as the mass on this side, that is the number of nucleons on this side and the number of nucleons on that side, that remains conserved. Also, the charge also remains conserved on the two sides, that is the number of protons or the number of charges, in fact the number of units of charge, they also remain the same on the two sides. So, both mass and charge, they are conserved in a nuclear process. So, if for example, the proton, sometimes if the energy allows this, that is we have beta particles which are, say, positrons which have high energy, then the proton can break into a neutron, a neutrino and a positron. You can see this is 1 unit of charge, this is 1 unit of charge, and the mass is conserved. The total mass on this side is equal to the mass of the proton. An example of such a process, you see, when we say total mass, we always mean mass energy. The Einstein's principle of mass energy, E equal to mc square. So, when we talk of mass, actually we are talking of the total energy. energy by c squared is mass. So, the total on the two sides would be found to be equal. Let us take another example. Sodium 22 with atomic number 11 becomes sodium neon 22 with atomic number 10 with the emission of a positron and neutrino. Positron takes away one charge, one unit of charge, therefore, this 11 becomes 10 and this 22 remains here as 22. So, the charge and mass is conserved in a nuclear interaction. What else does the unstable nucleus emit? Unstable nucleus can emit alpha particles. So, if XAZ emits an alpha particle, then its mass number is reduced by 4 because alpha particle has mass 4 nucleons and it has 2 units of charge alpha particle, and therefore, the emission of alpha particle means that 2 units of charge have already gone from this unit, from this nucleus. So, it becomes A minus 4 and Z minus 2 y, which is equal to 4 and this is the alpha particle. So, you can see A minus 4 plus 4 is A, Z minus 2 plus 2 is Z. So, the charge and mass is conserved. This is another example of such a reaction. Uranium 238 with the emission of alpha particle becomes thorium 234. So, 234 plus 4 is 238, 90 plus 2 is 92. So, both charge and mass are conserved. However, the emission of alpha and beta particles makes the daughter chemically different from the parent. You see, the atomic number has changed and therefore, the nature of this nucleus, its chemical properties have changed. So, beta particles makes the daughter chemically different from the parent, implying changes also in the electronic structure of the atom. Because the nucleus has changed, therefore, the atomic structure of the atom also undergoes a change. Although most frequent alpha, beta and gamma are not most frequently emitted are alpha, beta and gamma, but they are not the only particles emitted. As I said earlier, you can have positron emitted, you can have proton emitted and you can have a neutron emitted and so on. So, although these are the most frequent ones, the nuclei do emit other particles also. A nucleus has a complex structure. It has several energy states like an atom, ground state, first excited state, second excited state and so on. In the nucleus also we have such structure, ground state, excited state, second excited state and so on. So, a nucleus has a complex structure. It also has several energy states like those of the atom. The state of the least energy is called the ground state, just like in the atom. We have the ground state of the atom has the least energy. The emission of alpha particle or beta particle leaves a daughter nucleus in an excited state. You see, this I have told you earlier also. When the alpha particle or beta particle is emitted, then the daughter nucleus is most of the time in an excited state, that is not in the ground state, but one of the excited states, and then it comes down to the ground state by emitting gamma particles. Here we have example of rhodium 107. This emits a beta particle, beta decay it is called. It emits an electron and leaves the daughter nucleus in an excited state. The daughter nucleus is Pd and this is rhodium, and the emission of this particle leaves this nucleus in the excited state, and then it goes down to the ground state by emitting a gamma ray of energy 0.31 MeV. Beta decay leaves the daughter nucleus in an excited state, it comes down to the ground state by emitting a gamma photon. There is another example, cobalt. Cobalt 60 is again an unstable nucleus. It emits an electron or a beta particle. Its atomic number goes to 28 and of course, it emits an antineutrino and gamma photon. Where does the gamma photon come from? This leaves the nucleus, the daughter nucleus nickel, in excited state. Most of the cases it goes to this state, which then may emit 2 photons to come to the ground state, or in rare cases it goes to this state in cases 0.12%. It goes to this state, which comes down to the ground state by emitting the gamma of energy 1.33 MeV. So, there can be more than one gamma emission depending on how the nucleus decays. In this case, most of the time it decays by this route. This leaves the nucleus in this state, and this may come down by emitting 2 gamma particles. In rare cases, it leaves the nucleus in this state, which then comes down by emitting 1 gamma particle. So, in this lecture we have talked of the stability of the nucleus and the emission of particles like beta particles, alpha particles, gamma particles, and then the scheme of emission, how the gamma particles are emitted. The daughter nucleus is left in an excited state, and then it jumps to the ground state by emitting 1 or 2 or more gamma particles, depending upon where it is left after the emission of the particle. In the next lecture, we shall continue with this discussion of the stability of nuclei. We will find a reason why they are unstable, and we shall also find how one can picture the variation of stability of nuclei from the lightest nuclei to the heaviest nuclei. We shall see the binding energy curve, and we shall also see the processes of nuclear fusion and nuclear fission as sources of energy. And we shall, last of all, we shall conclude what kind of nuclei are actually stable. This is for the next lecture.